Okay. Can you hear me well? Is it too soft or too loud? No? It's good. Here we are. Okay. Okay, so I can start? Let's start. Okay, so yesterday, if you remember, we were looking at the different evidences of the existence of dark matter to convince ourselves that the dark matter problem is real and it's serious and it's on different scales, right? So we look at the small scales and we were looking at the intermediate scales. And in particular, what we're doing is that we were looking at galaxy cluster. And first we did the calculation of Zwicky, okay, with the virial theorem. Then we were like, okay, let's look at like different technique, complementary technique. So we're looking at how we can estimate the mass of cluster using X-rays, but this is useful to constrain the mass of the hot gas, which is most of the normal matter inside clusters, okay? And then we started looking at gravitational lensing, right? And so we did the calculation to derive, the Einstein ring and the different effects they were discussing were typical of strong lensing, and then at the end we were saying most of the situations we don't see all these like beautiful Einstein ring or these multiple images because most of the lensing that we deal with in real life is actually weak lensing, where we look at this small distortion and we study them statistically. Okay, but what's important is that the gravitational lensing is sensitive not only to the hot gas, but to the total mass. So you have hot gas plus dark matter, okay? Now, if we forget, in principle, if I look at a cluster and I imagine I have two independent techniques, right? And I imagine that the entire matter in the cluster is just normal matter. If I have two maps, the map of the hot gas and the map of the gravitational lensing, in principle, the peaks of the two masses should overlap. But in reality, this is not what happened. So the standard case is the bullet cluster, right? Where you have the map of the X-rays that is peak at the center, and then you have, so this is like X-rays, and then you have the map of lensing, gravitational lensing, where you have that most of the matter is actually spatially separated. And this is considered one of the strongest evidences of the existence of dark matter, which is very hard to explain with, for example, alternative gravity model like MOND, because it's very hard to explain why it's spatially separated, right? Why gravity applies differently, why is that? So this is one of the strongest evidence in favor of dark matter as new physics, and in particular it also gives us some information about the dark matter being massive, obviously, but also one important information that we get from the bullet cluster is that dark matter is collisionless, right? Because that's why it can just pass like without any problem, while the hot gas interact heavily, so it remains stuck there. This particle of the gas interact a lot, heat up, and emit X-rays, while dark matter doesn't care and just passes through with no interactions. Okay, so this is like an important, this tells us about the property of the dark matter. And the interpretation here is that the bullet cluster in reality used to be two clusters that 150 million years ago starting to merge, right? But now we have like one single cluster. Now I wanted to do the whole derivation also for the gravitational lensing for parameter like convergence and shear, which are two of the most important parameters that people deal with when you compute in practice gravitational lensing. If there's time, we'll do it at the end, because especially for the exercise of today, I think it's important to now discuss what are the observable signatures of dark matter and why we expect observable signature for dark matter. But if there is time, I think it's a nice calculation that rarely you see the whole thing explained, so we'll see. Otherwise, if we don't manage to do it today and you're interested, we have, I think, 5 to 6. We have, time to discuss, so you're always welcome to come to the office, or even tomorrow, after tomorrow. I'm here, okay? But let's see how it goes. Okay, so this is intermediate scale. So we convinced ourselves that intermediate scales we have a lot of dark matter. At the large scales, and here I'm also going a bit faster because I want to get to the observational part. We have, on the largest scales, we have the information, you know, the proof of the existence comes from looking at the large scale structure and from looking at the CMB, okay? So the idea is that when the universe formed at the beginning, we have this like hot soup, no? Quarks, leptons, and photons. And at the beginning, it's very hard for electron and proton to form neutral hydrogen because of a process called photodissociation, photoionization, actually. Okay? So at this point, the universe is like expanding and cooling down. And so the number of photons that have an energy that is above 13.6 electron volt, which is the binding energy of neutral hydrogen, becomes less and less and less. So at some point, it becomes energetically favorable to produce neutral hydrogen. Okay? So this is the moment when this process becomes inefficient, when the universe becomes neutral and transparent. So the universe becomes neutral and transparent. At this point, basically what happens is that before there is a before and an after. So before and after this moment. So before you have the electron, proton and photons, they are in thermal equilibrium. Okay. And after, the photons decouple. The photons decouple, and the universe is now neutral and transparent. Okay. And at this point, when they decouple, they can free stream. So they can just escape, they're free to move, and they're free to reach us. So this moment is what we called the surface of last scattering. Okay. And this radiation that reaches us, as you probably have heard in like some courses, is what we call the cosmic microwave background. Okay? Okay, so we can think really of the cosmic microwave background as a baby picture of the universe that was only 380,000 years old. So it's like baby universe here. And we know that one important property of the CMB, I'm screaming again, right? Yeah, very good. See? It's a perfect thermal black body. Okay? And so basically, when we look at the photon density, this is 1 pi squared, and then we have the energy of the photons, and we have the temperature, right? Now the temperature, the universe is keeping expanding, right? It's expanding even now. So the temperature of CMB evolve from now on as 1 over A, the expanding of the universe. So that means that at formation, so when we CMB form, at the beginning, it used to be, so formation, it used to be infrared like optical, but today it's in the microwave. And the reason is that because the universe is expanding. Okay. Good. Now, if one look at the angular power spectrum, if one look at the map of the CMB, a different spot, the angular power spectrum measures the correlation between different points in the sky. I'm not giving you many details today because we're going to study the angular power spectrum tomorrow and after tomorrow. We're going to do all the calculations. But the idea is that if we look at this quantity of the CMB, we can derive how much matter there is compared to normal matter, dark matter versus normal matter. And the other thing is also, so this is like by looking at the CMB, but I'm telling more tomorrow. And the other thing on the large scale is also just by looking at the galaxies. So the map of galaxies, how they are disposed in the universe, something that we call the cosmic web. So, you know, like the universe has this like beautiful map made of like galaxy clusters, which are the nodes. They are connected by filaments, and then there are all the different cosmic voids in between. And if the universe had no dark matter whatsoever, the large-scale structure would look very, very different. So really dark matter is responsible, it's sort of a glue, it's responsible for the map of the large-scale structure that we observe. Now, what's interesting is that, and this is sort of the conclusion in principle of the lesson of yesterday, is that we have proof of the evidence of dark matter really on like different scales, right? Because we said yesterday small scale, it comes from like galaxies. Now we look at like spiral galaxies, dwarf galaxies. On the intermediate scales, it comes from clusters of galaxies. And then on the large scales, we have CMB, we have the map of the large-scale structure. And we also use different techniques, right? Because we use the rotation curves, we compare with like gravitational lensing. And I mean, in the case of normal matter, we consider X-rays for like gas, okay? And for the large scales, we have the clustering dynamics, you know, the large scale structure and CMB. So different technique, different probes, different scales. They all agree on the same number. They all tell us that dark matter is about 5 times the baryonic matter. Okay. So the thing is that we know from all these different probes that there is a superabundant form of matter. We know where it is, because gravitation, with lensing, we know exactly where it is, how much there is, and we still don't know what it is, which is kind of a problem. Okay. So now, in the rest of the lecture today, we're going to try to understand what it can be, and more importantly, something that I'm excited about is how we can measure a signal. So now we'll go quickly over some models, but it will be very quickly because I want to focus on how do we detect a signal in practice. So what's the thought process? So the lesson of today is going to be a bit less calculation heavy than yesterday, but don't worry because we're going to make it up tomorrow and after tomorrow, where absolutely we'll have so many calculations that you will not want to see an equation again in your life. So, all right. So we start by delete here. But today is really about developing sort of like the intuition about how can we look for a dark matter signal, what are the things that we need to keep in mind to look for dark matter. Okay. So every time you listen people talking about dark matter, you probably listen them talking about dark matter candidates, right? There are some candidates that are more famous than others, and you might wonder why. You know, sometimes it's like a sociological issue. Some people are famous, and so their candidates become famous. But in reality, there are also like more scientific sound reasons why people get excited about a candidate compared to others. So now the question is, what makes a good dark matter model? That is like a reasonable question to ask ourselves. Well, a good dark matter model, first of all, it needs to explain the dark matter abundance. If I can't explain how much dark matter there is in the universe, then it's not really a model that I'm too excited about. So that's criteria number one. Criteria number 1, it needs some like theory motivation. What do I mean by that? It means that, for example, if I have a candidate that addresses multiple open problems, not just the dark matter, but maybe it solves something else too, or maybe I have like a different theory that has nothing to do with dark matter and predict a particle that coincidentally can also explain the dark matter, then people get excited because it feels more natural. Okay. And the third is that we want a dark matter problem, a dark matter candidate that is predictive and it's too low now. I get excited and then I start raising my voice. It's good or no? Yeah, now it's good. Yeah. You're gonna remember everything I say. Okay, so predictive and testable. Okay, testable. So basically, if I have a beautiful dark matter candidate where I do not expect any signal, observable signal, then people get a little depressed. Because we want to discover it, right? We want like a particle signature. We already have plenty of gravitational signatures. We need something more. So we really like a theory where we can predict some observations that hopefully we will test, we are able to test in our lifetime. Okay? Very good. So, in most of the course will be sort of like maybe some people, you know, like are agnostic in the and don't think about precise candidates, but in general, I think it's good just to mention what are some of the candidates that people are excited about. So briefly, I will mention a few of them, and I will tell you a little bit why people are like more interested in these candidates compared to like others, okay? So we do rapidly a bit of dark matter zoology. Here you go. Okay, the first candidate that we start with is like WIMP. These are weakly interacting massive particles. Okay. And the idea of WIMPs is that, in general, these particles, so let's see the properties of these particles. These are like massive. And when I mean massive, I mean particles that are in the GeV, TeV range. It's pretty heavy. And they interact with via gravity and via something that is of the order of the weak force or less. Order of the weak force or less, okay? Now, what are the theory motivation of WIMPs? Okay, so theory motivations. WIMP are, maybe you're still copying these, okay. WIMPs are predicted by many extensions of the standard model, where people were not looking for a dark matter candidate, they were just looking for extension of the standard model. An example of these is, for instance, supersymmetry. And the idea of supersymmetry is that for every particle in the standard model, there is a super particle that is more massive. So for instance, if we have a quark, you also have a squark. For every lepton, you have a slepton, and so forth, so on. We really know how to name things in physics. Anyway, the other, and if you want like a specific model of WIMPs, you can ask Nicolau and make him very happy. And you can look at minimal dark matter. This is like one example of a WIMP model. the example of the WIMP model, I've been told that the others should not even be considered, if you ask Nicolau. But you can ask him everything about it. And the second reason people are excited about WIMP is what we called the so-called WIMP miracle. So the WIMP miracle, the idea is that if you take a particle that has a mass, it is in the GeV-TeV range, that interact with a force that is of the order of the weak force or less, it naturally gives you can compute, if we have time we'll do it at the end, but for now you should believe me. Just putting this number naturally, you can compute how much dark matter you expect in the universe, and it's exactly the number that we observe. So that's why people call it the WIMP miracle, and that's why people are like super excited about it. Okay, but if we have time, we do the whole calculation of the abundance of WIMP, but for now, we'll see how it goes. Okay, now, so what do we expect from WIMP? Let me see. An interesting properties of WIMP is that if we look at the diagrams, I can do it. So you can have, for example, that you have like WIMP particles that interact and give you, for example, W boson, zeta boson. They can give you like quarks, and these quarks then produce something else. They give you, for example, pions, and these pions decay, and at the end of the day, you have a gamma ray flux. So remember the third criteria. There, I predict a signal. I expect WIMPs to create like signals that I can observe with my telescopes. So that's good. We like that. Okay, now a different candidate that people were excited about in the past, and now they're a bit less excited recently, just because it has been kind of excluded by many experiments, as explaining the whole dark matter. But another example is the sterile neutrinos. So we discussed on Monday, right, at the beginning, that there are so many open problems in the standard model. One of them is the neutrino mass. In the standard model, the neutrino is massless, but we do observe the oscillations, and neutrinos can oscillate only if they are massive particles. So people were looking at sterile neutrino also to explain why neutrino is mass. So we know that there are 3 species of neutrinos in the standard model: no E, no mu, no tau. And the idea is that there might be a 4th species or more. That's what we call the sterile neutrinos. Now, these sterile neutrinos do not interact via really anything really, with force, nothing, but they can do something interesting. And in particular, they interact in 2 different ways. What we call mixing or oscillation, where you have sterile neutrinos that oscillate into standard neutrinos, or they can decay. Okay? And so you have the sterile neutrinos decay into a standard neutrinos plus a photon, and the energy of the photon is roughly half of the mass of the sterile neutrinos. So for instance, if I have a neutrinos with a mass of the kiloelectron volt, I would expect an X-ray line. Okay, so again, predictive and testable. And then we have axions. Okay. Axions. So the idea is that axions were first proposed as a solution to the strong CP problem of quantum chromodynamics. Right? So this is the interaction between gluons and quarks. If we look at the Lagrangians of QCD, there is a term this one. These are the gluon field. Okay? So this is the Lagrangian of a strong interaction. There are many other terms, but let's focus on this one. This is the strong gauge coupling constant. And one thing that is interesting is that this term violate CP, there is CP violation, charge and parity. Remember, violate charge means that there is a difference if I consider particle or antiparticle, and parity is the symmetry when I take the mirror image. Okay, and one can show, I'm not going to do it today, but one can show that this violates CP, so that's at least a theory prediction. And one observation of this CP violation is a so-called neutron electric dipole moment, also called DN. Okay, so the idea is that the neutron electron dipole moment tells you if I have, so let me write here. So we know that the neutron is made up of 3 quarks, right? We have the up quark, and then we have 2 down quarks. And the neutron electron dipole moment basically tells you what is the massive, like if you look at the negative and positive charges, what's the angle between these particles? So in principle, if these are aligned, then theta equals 0. This is like the angular parameter that appears in the Lagrangian. But in principle, this is like an example, if they're unaligned. But in principle, theta is an angle. It can be anything between 0 and 2 pi. There is no reason why it has to be 0, right? So we have a theory prediction. The theory prediction, if you do the whole calculation, is that this electron-neutron dipole moment is of the order of 3.6 times minus 16. This is over the electric charge. Theta centimeter. So it depends on this parameter theta, which can be anything. And then, so this is theory. So this is the prediction from theory. And then the experiment, we only have an upper limit. So we don't have we have an upper limit from experiments, and we know that this has to be lower than basically 3 times 10 to the minus 26 centimeter. So this is an experiment. So you compare the two, and you derive an upper limit on theta, which is extremely small, 10 to the minus 10 or below. So that means that theta is basically 0. And now this is considered a fine-tuning problem in particle physics, because a priori there is no reason why this has to be exactly 0, and people were like, there must be a reason why this is it. There must be a theory that explains why theta is 0. And so what happens is that people were, I can put it here. People were trying to explain why this parameter is 0, and Pecha Quinn did what every particle theorist would do. They come up with a new symmetry. And when the symmetry is broken, a new particle arises. And then Frank Wilczek called it the axions, because there is a detergent called axions, because the axions washes away the strong CP problem of QCD. So again, we went from like quark and square to like laundry detergent. This is really like, I don't know how we name things in particle physics, but whatever. Now, what's important is that in the axial Lagrangian, we have a bunch of terms. I'm going to write some of them here. This is a strong coupling constant, 8 pi. So now the theta parameter becomes, instead of being a constant, becomes a dynamical field, which is what we call the axion. Fa is the energy scale where the symmetry is broken, okay? And then you have G mu nu, again the gluons. This is the term, well, I'll tell you later. Let me finish writing before. F mu nu. Here we go. These I don't write all the terms, so that's why we stay here until tomorrow. Okay, so this first term that I wrote here, this is the one for the case of the QCD axions, and this is the one that solves the strong CP problem. Because then what happens is that you have theta minus this term here, it becomes a theta effective, and you can explain why dynamically, when you go to the minimum of the potential, you can explain why theta is 0. So this is the QCD axioms, the one that solve both the strong CP problem and the Dark-Matter problem. And then there are these other terms that are present for the QCD axioms, but are also present for what we call the axion-like particles. So in the case of axion-like particles, this term here is not present, so it does not solve the strong CP problem, but it can still solve the Dark-Matter problem. Now, what about this other term and the others that I haven't written? So here we have the axion-photon coupling. Okay, so we have the axion field, and we have the electromagnetic strength field tensor, and its dual. So this is the interaction between axion and photons. And here I didn't write it, like all of it, but this is the interaction with fermions. Okay. So we do expect, by just looking at the Lagrangian of axions, we do expect that there is some interactions between axions and photons, and this is something that we can exploit to look for observable signature. Okay? F mu nu? Yeah, this is all mu nu. I mean, technically it's here, but yeah. Say again? Yeah. Technically, yeah. If you don't want particle physicists to be mad at you, put it up. And also GR people, they will be very mad. Okay, very good. So now let's look at possible axion-photon interaction and signature that we might expect. So there are three kinds of axion-photon interaction that we can expect by looking at this Lagrangian. One is one of the most famous, which is the Primakov effect. Okay, so this is the axion production in the photon collision with the solar and stellar plasma. So the idea, we charge particles in the solar and stellar plasma. So you have photons, we have your magnetic fields, these interact and they give you an axion. So you can produce an axion. Then you have what we call the inverse Primakov effect. These are all type of vertex that are allowed by the Lagrangian, right? Inverse Primakov effect, where you have the opposite, right? Now you have the axions that in the presence of the magnetic fields can convert into a photons. So now I have, I put it here, axion, then there is the magnetic fields, and at the end of the day, I expect the photons. And then you have the third case, which sometimes people overlook, and they really shouldn't, which is simple axion decay, right? Where you have now an axion that can just decay into two photons. That's allowed. This is more general if you want, because it applies to any kind of decaying dark matter, not just axions, but it also applies to axions. So there are many ways that you can expect like signatures, and again, like for example, if you have an axion with a mass of the order of the electron volt or sub-electron volt, then you would expect these photons to fall in the infrared optical window. So depending on the mass, you expect these photons to be in like certain wavelength. Okay. So these are like three examples of dark matter candidates that people are excited about, and I told you like why, and also why we expect to observe some signatures. Okay, so now what we want to understand is how do we look in practice for these particles. So whenever you, okay, let's start by looking at indirect detection, which is the whole point of this course. Okay. So in indirect detection, so when we talk about indirect detection of dark matter, what we really mean is the detection of signals in the cosmos that come from dark matter annihilation, dark matter particles, chi, standard model, right? They come from dark matter decay, where you have dark matter, chi, dark matter, I use it as synonym, standard model. Or when it comes to like any it can be like conversion, like in the dark matter conversion, like in the case of axion, right? Where I have like my dark matter candidate at some point, for example, Primakov happen, and I end up with like a photons, and I have like a conversion process. Or you can have any kind of interaction between dark matter and standard model particles. You can have, for instance, dark matter scattering, right? You can, for example, have the dark matter or like some particle scattered with like a particle in exoplanets or like a particle on Earth. You can use the Earth to look for dark matter, or particle in the sun, you know, and get trapped. So any kind of interaction the dark matter has with itself or with standard model particles that we study in the cosmos, we call it indirect detection. 5. Second. Yeah. Yes. I mean, obviously you need an underlying model. Yes, absolutely. Yeah. This is like when I put the point here, it means that some magic happens there. Okay. Okay, good. So the idea is that, and also by the way, I know that there are people that do like direct detection experiments. This is typically what you consider there, right? You have dark matter, it interacts with like one particle of your detectors, and you measure like the scattering. But you can do that in the astro environment in the cosmos too. Okay. Okay, now common assumption that we make is that dark matter is made up of new physics, and we have good reason, right? By looking at the bullet cluster and others, so dark matter is something new that is not part of the standard model of particle physics. Other common assumption is that it's stable, and then you might say, how can you tell me it's stable if you're telling me that we can look at decay signature? That's cheating. Sure, but you can also say it's long-lived, right? It's like it lived long enough that the decay rate, the decay lifetime is larger than the age of the universe, and so sure, it might decay sometime because there's so much, but there is still enough that we see the gravitational effects today. So it's either stable or long-lived. They're both good. And then we also have that common assumption is that it interacts somehow with standard model particles. And as a result of these interactions, we can expect really a wide variety of cosmic messengers. Okay? So it can produce cosmic messengers such as photons. So we have electromagnetic waves. We can expect neutrinos, or we can expect charged cosmic rays, or like nuclei, anti-nuclei. These are all like viable options. Okay, how much time do I have? Well, less than 5, it's 3 minutes. Okay, yeah. So let me delete that one. Okay, the last things before the break. Now, when we do indirect detection of dark matter, it's also important to distinguish between primary and secondary emission. Okay? So primary emission, again, it's like what I showed you before, right? You have dark matter, for example, that goes into WW boson or give you like Z boson or quarks, for example. And these can form pions. And pions can give you gamma rays. Or if you have pi plus, you know, then you can go muons, anti-muons, muons and nu muons. and then you have positrons and different neutrinos, or you can have pi minus that goes into muons, okay? And then you have, here you go. So these are all examples of primary stuff, or you can produce like proton, antiprotons, you know, from this kind of like primary channel. You can produce all sorts of things, deuterium, antideuterium. Okay, these are all primary emission. And then you have secondary emission. Because now let's imagine that your dark matter annihilates or decay, and at the end of the day you have electrons and positrons. And these electrons and positrons, they really like to interact in all sorts of ways. So one way is synchrotron radiation. So synchrotron radiation, the idea is that now you have your electrons, so you have a magnetic fields, there are many magnetic fields in our universe, and your electrons spiral in the magnetic fields. And when it does that, it also emits synchrotron radiation. So these are photons that you can produce, and this is an example of secondary emission. Or you can have that, for example, there are nuclei, you know, all the gas in our universe, so you have like a nucleus, and the electron is deflected. Remember, we talked about Bremsstrahlung yesterday. And then you have photon. So Bremsstrahlung radiation, it's an example of secondary radiation, right? Or you can have that you have your electrons, and then you have some photons, like low energy photons, and the electron is energetic and kick the low energy photons, transfer some energies, and at the end of the day, you have a high energy photons. So you go from like low energy to high energy. Just a passage, you know, transfer. And that's what we call the inverse Compton scattering. Okay. Can you give me some example of low energy photons in our galaxy? CMB, very good. What else do we have? We have dust in our galaxy. What do we expect from dust? Very good. And then what else do we have? We have stars, right? How do we? So you have a lot of like optical and like ultraviolet. So these are all examples of like low energy photons, and later I will give you like a practical example of how energetic they become after they interact with like electrons. Okay, so now I think it's probably 3 minutes have passed. Okay, good. So later we will see what kind of properties can we, if we observe tomorrow a signal from dark matter, we will understand how from like an observation of like one signal we can understand the properties, the different properties of the dark matter, and we will see like different examples with different cosmic messengers, okay? Very good. See you later. 5 minutes. Vabbè. 1, 2, 3, prova. Vabbè. Andiamo. Come vuoi. Okay, so can you hear me? Very good. Okay, so we've seen so far bunch of examples of dark matter models, and we convinced ourselves that we do expect some cosmic messenger from these models, okay? And then we look at what are the different signals, no? Like different primary, secondary emission. Now, what we want to understand is, let's imagine that we got lucky, and tomorrow we observe a signal. So what kind of properties can we learn by just looking at the spectrum, the flux observed from the cosmos? So one property that we can learn about is the mass of the dark matter particle. Okay? Dark matter particle. Because the idea is that if I have a flux, this is related to the energy scale. Okay? So the idea is that if I have the energy in the center of mass, in the case of annihilation, this is 2 mK. mK is the mass of the dark matter. In the case of decay, this is just mK. Okay. And so the maximum energy of your signal will be mK in the case of the annihilation, or it will be mK half in the case of decay. Right? So the energy scale, so if I have here the flux, I'm not putting units or anything, but I mean if you want, but it's qualitatively, no? So if I have a dark matter particle that has a mass of 100 GeV, I can be here, but if my particles is a bit lighter, 10 GeV, I don't have enough energy to reach 100 GeV, no, just conservation of energy. So the energy scale is determined from the mass of the particle. That's relevant also because if I'm looking, for example, at secondary radiation, electrons, to have secondary radiation, I need to produce an electron in the first place. So if I have a particle that has a mass that is less than, like an MeV, if I study electron volt scale dark matter, I don't have, my dark matter particle is too light, it's not heavy enough to produce an electron, so I will never see secondary radiation from very light dark matter in general, no? I mean, you can have like super fast, but no, you won't see it. Anyway. So basically, the mass also determines what channels are open. The second thing, some of you were asking me during the break, is how you link that to the parameters in the Lagrangian. So the parameters in the Lagrangians, they give you the strength of the interaction. Okay? Right? And that's related to the amplitude of the signal. So for instance, if I'm looking at annihilating dark matter, my flux, so here I have the flux, here I have the energy of my photons, no? Now, if I have that this particle have a cross-section that is, for example, 3 times to the minus 24 centimeter cubic over seconds, it will be here. If I have something that is orders of magnitude less interacting, like for example, this is like 2 orders of magnitude less interacting, it will be down here. Okay, so the idea is that the larger the cross-section, the larger the flux. If I look at decay, then it's the decay rate. So the larger the decay rate, the larger the flux. Sometimes people, instead of using the decay rate, they use the decay lifetime, because that's more intuitive, right? So the decay lifetime is the inverse of the rate, but that tells you how fast they decay, just more intuitive. But in this case, the larger the decay lifetime, the smaller the flux. So just keep that in mind. Say again? You can, basically when you look at a signal, from looking at the normalization of my signal, I can derive how strong the interaction is. If I have a small signal, that cannot be due to a very strong interaction. So these are properties that we can get just by measuring the flux. So by measuring where the signal ends, I can tell you more or less what's the mass scale. By measuring how big the signal is, I can tell you how strongly they interact or how fast they decay. Or, for example, in the case of axions, what we care about is J gamma gamma, right? And so I can tell you how fast and how efficient they convert into photons, right? So these are all information that I can just get by looking at the normalization scale. But then there is another thing that sometimes people sort of maybe hide under the carpet a bit, which is there is also the information on the final states, right? Let me be more specific. So this is related to the spectral shape of your signal. So if I have, a flux, so this is my flux, phi, flux, okay? This is the energy. If I have something that goes like this, maybe it's BB bar. If I have something that goes like this, you have like electrons. If I have like a spike, it's going to be decaying into photons. So by looking at the shape, I can tell you what's the channel. But there is a caveat. So typically, each channel should be weighted by the so-called branching ratio. So if I have the total energy spectrum is the sum of the branching ratio for the different, these are all shy chalk. I don't know what's going on. Here we go. Now you can see it. Now, where you can have, maybe you have that 50% of your dark matter decay into BB bar quarks, 50% decay into electrons and positrons, and you have the branching ratio that is half, no? The point is that people usually don't really consider that, and people usually consider branching ratio 1, and what they will do is that they will just say, okay, what happens if all the dark matter annihilate or decay into BB bar, all the dark matter decay into electrons and positrons, unless you have a very specific model that tells you, I expect 20% into plus E minus, 20% into whatever, okay? But that's not a big issue in the sense that it scales linearly. So if you have, if instead of having the dark matter, 100% goes into electrons and it's half of that, you just rescale. I mean, that's, so just keep that in mind, that usually this is an assumption that people make. Okay, cool. So now we know, if we observe a signal, we know that we can really learn a ton, really a lot, by just looking at all these properties of the signal. Now, the thing is that if we observe a signal, how confident are we that it's dark matter, right? So in other words, can we discover dark matter with indirect detection? And I mean, the answer is yes, otherwise I would do something else with my life. But how can we discover dark matter with indirect detection? Well, one way is to look at unique signatures from dark matter. So people, for instance, like lines a lot because of that. Okay, so some like specific, like imagine that I have a model that predict a signal that has a peculiar shape or something, very different from what we expect from like normal matter. Now the problem is that when you look in the cosmos, remember the first lesson, the enemy, we have the astrophysical background. So one way is that we want to be good at modeling the astrophysical background, right? So we can all become part-time astrophysicists and try to be as good as we can and understand the astrophysical background where we're looking for the dark matter signal. Or another way is that we can use like a promising targets and like environments where, for example, the astrophysical background maybe is expected to be very, very low. So Friday, I will mention, for example, cosmic voids as an example. Today, maybe not, I don't know. We will, if I have time, I will mention like cosmic filaments. as a promising environment. So we can look in places where, the dark matter signal is expected to be either larger or qualitatively different from the astro signals. Okay? Okay, good. Now, yesterday, some of you were wondering about the rho squared in the J factor, stuff like that, right? So we'll do it. We'll derive it today. How we expect? What's the flux? Like how intuitively we write the flux that we expect from annihilating and decaying dark matter. Okay. So flux. Boom. Okay. Now the annihilation probability per unit of time for one particle is nx. This is the number density of dark matter particles. Okay, so this is centimeter to the minus 3. Then you have sigma and v. So sigma is the cross section. So that tells you cross section. So that basically measures how likely particles are to interact when they meet each other. And this is sigma squared. And then you have the velocity, the relative velocity, because faster particles meet more often. If you go faster on the highway, bad things happen. Same things happen to dark matter particles, just they're not really alive, so who cares? Okay, now, important thing to keep in mind is that dark matter particles do not all have the same speed. There is a distribution, right? And so typically, they don't have all the same velocity. So there is like a phase space distribution that depends on the velocity. For halos, people usually assume a Maxwellian. But what the reason I'm telling you is that in papers, you always find this sigma v in these parentheses because you take an average, because they don't all have the same velocity. And this is just defined in this way. Okay, FV1, here we're being very generic so far. So whatever space phase distribution you want for them. This so far is very generic. Okay, very good. Now, okay. Now, annihilation is a two-body process, right? There are two particles involved. So the number of particles in volume V is nx times the volume. But that means that the number of pairs, because annihilation, two particles, this scales as n squared dark matter, b squared. Now, the annihilation rate per volume, this is sigma v, because that tells sigma v tells you how likely they are to interact. And then you have n dark matter and n chi bar. And now you can consider two different scenarios. One scenario is the case in which dark matter is a Majorana particle or self-conjugate. So now you have chi equal chi bar, right? And if that's the case, then the annihilation rate is 1/2 sigma v n squared chi. Why? Because you want to avoid double counting. Like ij is equal ji. Okay, good. But then you have the other case in which that's not true. And so now you have the case in which you have a Dirac particle, and that's different because now you have to use these things here. Now we remember that the density is mass m chi n chi plus m chi, well, m chi bar, but usually you expect that the mass is the same. So m chi bar is the same, but you might have a different number density. And now typical assumption is that actually the number density is the same, because unless you have a specific model, you would expect that chi and chi has the same number density. So that's standard assumption. And if that's the case, then m chi is well, these, but now this is the same, we said. And so this is 2 m chi n chi. And so now we can write n chi as rho over 2 m chi. And so if that's the case, then we can write the rate here as sigma b, and then we have rho squared, rho over 2 m chi, and this is 1/4 sigma v m chi squared, rho squared. So if you do the same in the case of the Majorana, you can see that there is a factor 1/2. So basically the idea is that Dirac gives half the annihilation rate for the same rho. So that's also something that people don't tell you usually, but when they show you like the two, they usually assume the highest one, but there is a difference of 1/2, so people usually don't care much. Okay, good. So that's where you have the rate, and then soon we'll also arrive to the J factor, but you can already see sort of like where this is coming from. Now, each annihilation, okay, I don't need this. Now, each annihilation produces a spectrum, dn de. This is the number of particles per annihilation per energy. Good. And now you can link this to the emissivity. Emissivity. Sometimes people call it the source function. Pick your favorite. The emissivity Q, it's sort of the same thing of yesterday when we were looking at KV for Bremsstrahlung. Same idea. This depends on E, it depends on the position. And this is, in principle, is the rate, you know, so how much these things are interacting. And then you have the spectrum, right? Now the emissivity, so if you substitute, it's 1/2 sigma V m square chi rho square chi dn de. Because between the two, people usually assume the one that gives you the highest rate. That's the typical assumption. Because why would you renounce to 1/2? It's already hard to detect. Let's be optimistic here. Okay, good. So the decay, so this is for annihilation so far. In the case of decay, then it's easy in the sense that it's just n chi over tau instead of like sigma b, because now they are decaying the particle. And so the rate is like rho chi m chi over tau, right? And so Q, the emissivity in the case of decay, is just 1 m chi tau rho chi dn de. Okay, now a good skill that every physicist should have is dimension analysis. It's a good skill to have in life. So now, if we look at Q annihilation, for instance, we have, what do we have? We have sigma cube over second. It's sigma v, right? Then we have the mass. This is like GV squared, right? And then we have rho. What's rho? Rho is GV, because it's like mass. And then you have volume. So sigma to the power 3. But this is to the power 2, because it's rho squared, right? And then we have dn over de. So now we have GV. Okay? So that means that when you cancel everything, you end up with like seconds, centimeter cubic, GV. Okay? Now let's do the same for decay. Do the same for decay. And now we have 1 over mass, GV. We have tau, which is in second. We have rho this time, not rho squared. So now we have rho is a density, right? So it's GV, mass over volume, centimeter cubic. And then we have again the NDE, 1 over GV. And look at that, amazing. Same thing. That's like an easy way also to check that the formula that you remember correctly, because it gives you exactly what you expect. So even if you remember just for one and not for the other, it allows you to move easily. It's a cross-check, you know? Like, it's usually a consistency check that is good for physicists and sort of makes a big difference between a good physicist and a bad one. Okay, good. Yeah. Yeah. Chi. Yeah, I mean, it's a, yeah. What do you mean? You mean if I use a X or chi, I use like a... What do you mean? Ah, it's like 2, you mean? What's a... What are you... What am I missing? What's the typo? What's going on? We're happy? We're happy, okay. Okay, now we want to get to the flux. We're almost there, guys. And to get to the flux, I need to delete. Okay, so the number of particles that is emit per time, okay? So number of particles per time, the dot means per time. It's like the NDT if you prefer, okay? Per volume element and energy interval, this is just Q, so the emissivity, okay? And then dV, dE, so this is in the energy interval between E and E plus dE. And now the differential, so the emission is isotropic typically, because why would it not be? So it's isotropic emission where I annihilate, goes everywhere. And the observer is spread over a sphere of area 4 pi s squared. S is like the line of sight, because remember, even from like Monday, we measure things along the line of sight. We are special observers here. Okay, so the differential flux at Earth, the one that we measure, is 1 over 4 pi s squared, and then we have Q, Ex, dV, dE. Now dV is s squared ds d omega. S line of sight, omega is the angle. So that means that d phi dE E of the photon, or like whatever messenger you're considering, 1 4 pi, and now you have the integral over the line of sight of ds q Ex. So this is the differential flux. Now, when we substitute, now we have the for decay, so let's do it here. Now, for annihilation, when we substitute, we have the d phi. Do I have enough space? This is a long formula now. Okay, d phi, is it too small for you from the back? Probably. Okay, so let me write it here. Because we need to substitute this, right? So let me write it there. So now we substitute, and I'll try to write it big, because that's the final formula now, right? So if we have this equation here that depends on the integral of the line of sight of the emissivity, we have annihilation, we substitute what we just derived, and we have the d phi dE d omega is 1 over 4 pi sigma v 2 m squared chi, which is written as an x, but it's chi, dN dE, and now you have the integral over the line of sight of rho square chi. And this is what we call the J factor. Okay? Now in the case of decay, so decay, d phi dE d omega, this is 1 over 4 pi, 1 over m chi, tau, just substituting here, dN dE, and then you have the integral of rho chi. And this is what we called the D factor. Now intuitively, this makes sense, and it comes from the assumption that annihilation is a two-body problem, decay is a one-body problem. That's why we have rho square here and rho here. But it comes from the beginning when we consider the rate. Sometimes people consider the integrated J factor in the sense that if you want d phi dE, because imagine that your telescope observes a 3 times 3 degree region. So now you have an integrated flux. So at this point, this will be the d omega, d phi, dE, d omega in a certain region, the omega. So in certain cases, people write the J factor and the D factor, the integrated one. So you might see people talking about J delta omega, which is basically the integral over the omega of ds rho squared. People, for example, do it when you look for dark matter like in dwarf galaxies, because you have a certain dimension of the dwarf galaxies, whatever. I mean, in one case it's like d phi dE, in the other case it's d phi dE d omega. It's an extra integral. Okay. Now, how much time do I have? 12 minutes. Okay, I think I prepare enough material for like 2 courses, but it's okay. Okay, so we'll, let's see, what do we do? Okay, now I'll tell you something. Okay, so remember before when I was talking about the mass, no? That depends, like the energy range. Okay, so if we have the mass here, no? And we have TV scale, we have GV, we have MeV, we have keV, and we have electron volt. Okay, the mass determines the scale. So if we look at prompt emission, very massive one, you expect gamma rays. You can produce gamma rays. If you look at MeV, MeV can still do some soft gamma rays, but MeV you can produce X-rays. You can also, I'm not putting all the neutrinos, you can do that too. Let's focus on photons now. But then when you arrive at the kiloelectron volt, the gamma rays, you forget about it. You're left with X-rays. And if you go electron volt scale, yeah, also the X-rays becomes complicated. So now you have infrared, optical, starlight, all that stuff. And if you go lower, here you're left with radio. That's primary. What about secondary? So when you are at GV and TV, you can also make electrons and positrons. Good, because these electrons and positrons can do inverse Compton scattering synchrotron, for instance, and they can give you X-rays and radio, for instance. They can give you all the others below, and same here. Electrons and positrons, and so you can have all the secondary radiation. But here, you don't have electrons and positrons, so you do not have secondary radiation there. Okay? So in general, when you look at like MEV and above, you have like all sorts of like signals that you can study, while below, you have a bit less, but that's okay. Okay? This is just like conservation energy, you know? Now, when it comes to like indirect detection of dark matter, you should always ask yourself a few things. One is like what candidate you are considering. You can also decide that you want to be agnostic, and you say, well, I'm just considering the annihilation cross-section, the decay of time, I'm not thinking a specific production mechanism. Fine. But then, so at least you have to ask yourself, like, okay, what mass am I considering, you know? Then you have to consider like what kind of signal am I looking, right? If it's X-rays, radio. And once you have decided that you're looking into like X-rays, for instance, or radio, then you have to ask yourself, what's the astrophysical background that you should be worried about? Because different wavelengths have different sources that bothers you. And you also have to ask yourself what telescope you should use. Because we are doing physics here. And so we have to ask ourselves, how do I observe such a signal? And different bands have different telescopes for good reasons. For instance, If you look into X-rays, or let's do gamma rays. If you look, where is, here we go. If you look into gamma rays, typically people divide between low energy, high energy, and ultra high energy, or like very high energy and ultra high energy, whatever. So this is like 0.1 E gamma 30 MeV. This is like 30 MeV E gamma 100 GeV. And this is above 100 GeV. So the idea is that different frequencies needs different detection technique. So if I look into, let's step back one moment. If I look into gamma rays, you know that the atmosphere is opaque. We have an atmosphere that protects us, which is great. It's basically due to, like, there is water vapor, there is carbon dioxide, and there is ozone. And this is why we cannot observe certain frequencies from Earth, right? We cannot observe gamma rays, we cannot observe X-rays, and typically we cannot observe UV, which is a good thing, because if UV, you know, burn us, imagine if we have like a gamma rays right on our head. It's not gonna be nice. So that's a good thing, so we are protected, but it's also why we need satellites to study these ones. Where then there is atmospheric windows, which is basically like a visible light, an infrared, that we can study from ground. And radio, most of radio, the long wavelength we cannot. But then you also have the very high energy gamma rays. And the very high energy gamma rays, they're interested because we can actually study those from Earth. So now, I'm gonna do that quickly. So the idea is that for GeV, so for GeV and high energy, you know, this one, we need satellites. That's why we look at Fermi and stuff like that. But for ultra energy, we can exploit the Cherenkov radiation. We have Cherenkov radiation. And so you have the air Cherenkov radiation, ACT, telescope like Veritas and MAGIC. And then you have the water Cherenkov. And the water Cherenkov are different. The water Cherenkov are stuff like HAWK. And this telescope, they all look at water Cherenkov radiation, but in different ways. The air Cherenkov, the Cherenkov radiation, you remember what's the Cherenkov radiation? You know, when a particle is like V, like you have the velocity C over N, so a particle that is moving in a medium change the velocity, it can go faster than the speed of light. And that emits Cherenkov radiation. So in the air Cherenkov radiation, the Cherenkov radiation is produced in the air. In the water Cherenkov radiation, these are like super energy particles that reach the detector, and the Cherenkov radiation is produced in like water, like tank full of water. Now this might seem to you a problem for, I don't know, engineers. Why would I care? But that's have like a very important specification for us. Because when you look at air Cherenkov telescope, these are like sensitive to high energy, like TV scale. They typically have a narrow field of view, 3.5 degrees, and something very annoying, they only operate on moonless, clear nights. Okay? Because Cherenkov emission is very short, nanoseconds, and it's very weak. So if you have the moon or the clouds, you're screwed. It just saturates your detectors. While if you look at water Cherenkov array, it's a different story. Because these are also sensitive to very high energy, but well beyond the TV. Okay? They typically have a large field of view, and they scan the sky 24/7. Because the Cherenkov radiation happens in the detector. So they don't care about the moon. They are not vampires. Okay, good. Then The other thing that you should always ask yourself, so this is an example for like gamma rays, but same like you have X-rays, you always have satellites. In optical, you have both. People go like, you have satellites and you have like from Earth. The other thing that you should always ask yourself is like where to look. So the idea is that people usually look at things like the galactic center. You know, what's your target? I have a particle that I want to explore. I know what kind of signal I expect. I expect gamma rays, X-rays. Now, where do I point my telescope? You can point your telescope at the galactic center. You can point your telescope at dwarf galaxies. You can point your telescope at a cluster of galaxies. Now, these people like these because you have a lot of dark matter. Remember, we discovered the existence of dark matter from these guys, right? But there are also big problems when looking at this. One, galactic center, you did it like yesterday, right? The exercise, how it changes with different profile. So you have a big theory uncertainty based on the profile that you assume. Also, the galactic center is the favorite place for baryons. So your astrophysical background is huge. From dwarf galaxies, you have a lot of dark matter. 5 minutes. Yeah, it's okay. You have a lot of dark matter, but you also have a big of uncertainty, especially for the ultra-faint dwarf galaxies. Because in the ultra-faint dwarf galaxies, so the way that we know how much dark matter there is in a dwarf is that we study the movements of stars. The dynamic, remember, like what Vera Rubin did, where I look at the, how stars move. But now, if it's very luminous, means that I have a lot of stars. I'm very good at like measuring. I have a huge statistics. But if I have like 5 stars, and for some reason, I screw up with one, that makes a huge error in the estimate of how much dark matter there is. And cluster is also like they're very luminous. So people are now starting to look elsewhere. So some places that you can look at is like blank sky. So this is something that is very known. Every astronomer knows about blank sky, and particle physicists do not know about their existence, which is why we need more people, more astrophysicists and particle physicists talking to each other. But the idea is that when an astronomer looks at their favorite stars, because that's what they care about, they also look next to it. And the reason they do it is for background subtraction. So they want to know how much light is coming from the stars of the galaxy. They need to subtract what's around. So that means that all astronomers take all these blank sky, which are great because there's no bright sources there. So there is plenty of these with like telescopes, but you need a spectrograph for this type of things. People look into, for example, cosmic filaments. So this is like, you have clusters, and these are the structures that connect filaments. Again, usually astronomers study filaments for something that, because half of the baryons, remember, we have 5% of baryons. Half of them we don't see. So this is called the missing baryon problem. And the leading solution of the missing baryon problem is that they are in this warm, hot intergalactic medium in filaments. So astronomers study filaments for that. But one can show that filaments are dark matter dominated structures. So most of the matter there is dark matter. Or you can look inside cosmic voids, we will mention after tomorrow, which are these like big, huge, like places in the sky where there's very, very little matter, but there is still like tons of dark matter there. How much do I have? At this point, how hungry are we? It should be 0. No, that's okay. That's a good point to stop. So that's, yeah, I mean, I wanted to give you like examples, but I won't. And if people are interested, I mean, you will do exercise about inverse Compton, right? So, which we discussed, how we measure the signal. So you will see some of it this afternoon. And if you have questions, you're welcome to ask any point. Thank you.